yours.
All right, well, thanks so much for coming to my talk today. This is joint work with Shwayman Ba, who is a Penn student who graduated last year and is now at Pittsburgh, as well as Alex Emas at Chicago Booth. All right, so today we're going to look at a simple belief updating task in order to try and understand what sort of biases may emerge in the way that people react to information. So just to give you a sense of the paradigm, we look at a very standard belief updating setting. Let's suppose, for example, there's 100 cards. Either card either says earn A or earn B. A card is drawn from the deck, and then based on whichever card is drawn, a ball is going to be drawn according to a different distribution. So if earn A is drawn, there's going to be one urn with a certain number of red and blue balls. If earn B is drawn, there's going to be another urn with a different set of red and blue balls. And so what people are tasked with doing is reporting what their belief is about the likelihood of each urn after they observe a ball. So if they see a red ball, they say, what's the likelihood of urn A versus urn B? Or similarly, if they see a blue ball, they say, what's the probability that urn A versus urn B was chosen? Okay, so this is a very simple task for people who know Bayes' rule. You should say, how should you update your beliefs? Well, there's a straightforward prior. Let's suppose there's 50 urn A cards and 50 urn B cards. Let's suppose we also told people there's 70 red balls in urn A, the remaining 30 balls are blue, and urn B is just flipped. There's 30 red balls and 70 blue balls. So they had this information, they had a prior, they had information about the signal structure via the number of balls in each urn. Then Bayes' rule would just have a straightforward formula to figure out what's the probability of urn A conditional on seeing a red ball. Right, but if you look, there's three key features of this information structure, this informational environment that agents need to take into account when they're forming their beliefs. The first is this prior. Here it's a uniform prior. Each urn is equally likely. The second is what we call the signal diagnosticity, and that's the probability of a red ball conditional on the urn, either 0.7 or 0.3. And then the third thing is the complexity of the state space. So here there's two urns or two states that they're forming beliefs about when they update their beliefs. And so what we want to do in this simple setting is try and understand how these three different features of the informational environment potentially impact the biases that emerge when people are forming their beliefs. Right, what we're going to show is that we can theoretically model belief updating via several different psychological mechanisms and predict how variation in these three components of the information structure interact with whether agents overreact or underreact to information. So this is the exact paradigm that we're going to use in this paper, this paradigm with cards and urns and balls. And it's a really nice paradigm because it's reflective of different settings, such as updating about a stock after you see an earnings announcement, or updating about a candidate after you see, let's say, a signal of their quality. But it's a really simple paradigm where we can control the information environment and use it to study a broad set of learning environments. Right, so as I said, this is the Bayesian benchmark. If we look to the literature on how people react to information relative to this objective benchmark, there's been mixed evidence. So there's been some papers that have found evidence for underreaction, or that people don't move enough in their beliefs. They stay too close to the prior. They don't react enough to information. And then there's also been another literature that has found that people tend to overreact. So they react too much to the signal. They don't keep the prior as much in their beliefs. Their beliefs move too much relative to the Bayesian benchmark. So we've seen this inconsistent evidence, and one of the goals of this paper of having this nice paradigm that we can manipulate the different dimensions of the information structure in while maintaining an objective Bayesian benchmark is that we can try and see, are there key features of, say, the signal structure or the prior or the complexity of the state space that are leading to these differences in underreaction versus overreaction. Right, so just to summarize the literature, there's been a lot of evidence from experimental studies in the lab. They've mostly found underreaction. Looking to a survey article by Dan Benjamin from 2019, he concluded that the experimental evidence on inference taken as a whole, suggests that even in small samples, people generally underinfer rather than overinfer. And in contrast, if we look at the literature from finance and macro, we look at a survey article in that literature, there's exactly the opposite conclusion. So to quote from a survey article by Bordal et al. In 2020, the expectations of professional forecasters, corporate managers, consumers, and investors appear to be systematically biased in the direction of overreaction to news. All right, so this is just to give you a sense that literature was conflicting between lab studies and finance and macro. There really wasn't a clear sense of why do we see underreaction in the former, but more overreaction in the latter. Right, so that's what one of the goals of our paper is, to try and reconcile these disparate findings. Okay, so what's our approach? So we first have a theoretical model of belief formation. We look at a setting where the agent has a two-step belief formation process. So before processing the information to form beliefs, they first determine what features to attend to or pay attention to. And then after they figure out what to pay attention to, they're going to then process their information. And so how does this come into play when we think about attention? Well, this is where complexity comes in. When facing a more complex learning environment, attention is going to be more constrained. And so agents may be more likely to simplify their information structure before they form their beliefs, because it's more difficult to pay attention to many different states than just the smaller number of states. So this is suggestive of evidence from the rational inattention literature, as well as the behavioral inattention literature, showing that agents first may try and simplify the informational environment and then form their beliefs in this subjective, form their subjective beliefs within this simplified environment. All right, so that's what we call our first stage, or the channeling stage. Attention is going to interact with complexity. Right? We motivate the idea that complexity matters by looking at the psychology literature and saying working memory has a fixed capacity. People can attend to a limited number of objects. And so with multiple states, there's more to pay attention to. There's more different states that you have to try and think about how to form beliefs over when you're forming your belief, your posterior belief. And so attention may be directed more to some states rather than others as the number of states increase. So that's how we operationalize complexity, in our case, through the number of states in the information structure. Right, then we say that, how do agents decide what to pay attention to? Well, here we look to the literature by Bordallo and Schleifer looking at salience. And the idea is that agents will channel their attention to the states that are relatively more likely given the information that they see. So if they see, for example, a high earnings announcement, that would be suggestive of a firm that had a high fundamental value, versus if they saw a low earnings announcement, that would be suggestive of a firm that had a low fundamental value. So in that sense, looking at the representativeness or salience of the information determines how they channel their attention. All right, then the second stage after they've channeled their attention is they process their information to form beliefs. And here in this stage, we assume that agents apply Bayes' rule, but with cognitive noise. So cognitive noise is motivated by the literature from going back to Green in psychology in the 60s, more recently developed in economics by Michael Woodford and others. And the idea is that agents have a prior on their information structure parameters. So you tell them things like the prior belief, the signal structure, but they process that with noise. They don't fully internalize what those parameters are. So they have a noisy representation of this informational environment. And what that does is it sort of mutes their reaction to the information relative to the true parameters. All right, so they use Bayes' rule, but it's going to shade things towards the prior or make them more insensitive to information. All right, so what we do is we show that, first of all, theoretically, we combine these two psychological mechanisms, and we show that, and then we generate predictions on posterior beliefs based on the interaction between these two mechanisms. And then, given our model of belief formation, we derive comparative statics on how those three main properties of the information structure, so complexity of the state space, signal diagnosticity, and shape of the prior, interact with these two psychological mechanisms in determining how beliefs are formed, and therefore whether agents are under or overreacting. Right, so what we find is that in our model, overreaction is predicted for more complex state spaces, priors that are more concentrated on intermediate states, signals that are noisier, and signals that are surprising in the sense that the prior is really strong in favor of one urn, and the signal is very strong in favor of the other urn. In contrast, underreaction is predicted for more simple state spaces, so their channeling attention has less bite, cognitive noise has more bite. Similarly, diffuse priors, where people put more weight on extreme states ex ante, more precise signals, and signals that are confirming or when a prior puts a really high probability on one state, the signal confirms that prior by also supporting that state. Right, so this is our theoretical model. I'm going to present it in a minute, but we generate these predictions, and then we can test them in the experimental paradigm with the balls and the cards, balls and urns and cards, by manipulating the different features of that paradigm and measuring agents' beliefs and seeing if they confer with our predictions from the theoretical model. Okay, so we find in our experiments that indeed they do. The data matches the theory really well. First of all, this can explain the pattern of over versus underreaction documented in experimental work. So as I said, most experimental work has found underreaction. Turns out that one of the key features of those experiments is that they generally looked at two-state settings. So looked at settings with two urns. And in general, our model predicts underreaction in those environments. They're simple, so the channeled attention doesn't really have much effect. There's not much effective channeled attention if you only have two states that you're deciding to channel attention between versus a more complex state space. But there the cognitive noise comes in, which is pushing people towards underreaction. Whereas in contrast, financial markets, the data in financial markets was often a much more complex environment. So people were forming beliefs over the fundamental value of a firm, and that fundamental value could take many different values. It could be high, it could be low, it could be intermediate. In those complex environments, really the channeled attention comes in, and that's where more overreaction is predicted. So it's, first of all, it reconciles this evidence, and second of all, it suggests that the use of two states in the lab was not without loss of generality. It was giving us results that did not extend or did not have external validity in environments beyond two states. Also, given complexity in real-world settings, it suggests that we may often see overreaction as we do in macro and finance, because settings with more complex state spaces are generally leading to more overreaction. All right, so let me just jump right into the experimental setup. What I'm going to do is I'm going to describe the experiment first, and then I'm going to show you the theoretical model. And this way, I can go back and forth between a prediction of the model and then the experimental results, so you can see those two side by side. All right, so just to start with the experiment, we had a pre-registered experiment with over 2,000 participants on Prolific, which is an online forum that people often run experiments on these days. We did a series of attention and comprehension checks just to screen out people who were not paying attention or did not understand the informational environment. We did incentives. They received a $2 base fee and a $10 bonus if their randomly selected answer was in 3% of the Bayesian posterior. So they were incentivized to predict the Bayesian posterior based on the information that they observed. They answered between 8 and 15 questions each, presented in random order. This 8 and 15 was to ensure that we didn't overwhelm them, so they were still paying attention or reasonably processing these questions, even up until the end. And then the three things we varied, as I just mentioned, are the complexity by varying the size of the state space or the number of urns, the diagnosticity, more or less informative signals, by varying the number of red versus blue balls in the urn. So we always looked at a binary signal environment. There could be multiple urns with multiple different combinations of red versus blue balls. The diagnosticity always corresponds to how many red versus blue balls there were in a particular urn. And then lastly, the concentration of the prior, which is, so the state space was always ordered in terms of the number of red balls from low to high. And so we could vary the concentration between the extreme states, which had a more uneven number of red versus blue balls, versus the middle states, which had a more even number. Also, in the case of a binary state space, we could vary the symmetry of the prior by having it either be uniform or having one of the states be more likely than the other. All right, so those are the three parameters along which we're going to vary in the experiment, and then see how beliefs respond to beliefs, and therefore over versus under reaction responds to variation in these three treatments. All right, so just to give you a sense of what subjects saw, this is the design. They were first described the information environment, so how many cards there were, what information they would have. They were then shown this picture to give them a sense of the timing. So first there was cards, the cards were drawn to give them an urn, and then they would see a ball, either red or blue. And they understood as well the sequence of events. So there was 100 cards, each with equal probability. If urn A card is drawn, urn A is selected, so on and so forth. Then they're told there's 100 balls, and again, each ball is going to be equally likely to be selected. All right, so then they were given their task. And so here you can see the state space is going to correspond to the number of different urns. So in this example, there's 3 urns, urn A, urn B, and urn C. We can see that we're setting up the prior by telling them the number of each cards that say urn A versus urn B versus urn C. So this right here would be a prior where there was more mass on the middle, 50 cards were the middle state versus 25 were either of the end states. Right, so urn A had 60 red balls and 40 blue balls. Urn B was 50-50 and urn C was 40-60. So these 3 things we varied: the number of cards, the number of urns, and then the number of red versus blue balls. But it was always made very clear to subjects what they were seeing before each belief task that they engaged in. All right, so this is, as I said, the prior and then the diagnosticity. All right, so this is how what the experiment saw. The theoretical framework is going to be basically mapping this experimental design into a standard informational environment. So let me go through that next, and then we can start talking about the predictions.
Can I ask one question about the clarification about the experiment?
Yes, of course.
So you said you pay them according to how far from Bayes' law their predictions would be. So how do you exactly do that? I'm curious.
Oh, so this is, as you can see, one of the nice things about this paradigm is that there's always a clear Bayesian benchmark. So we could calculate that, and then if their answer was close enough to the Bayesian posterior, then they receive the bonus.
So you're asking them about a belief about the different cards. So which card they're facing, which urn they're facing, or what? Or
yeah, we elicit their full posterior belief over each urn. So they would have a box under each urn, and they would put in their posterior belief, and then it was imposed that they had to sum to 1.
And then how do you? I mean, so and then how do you tell them that you pay them? So you say you pay them according to how correct this is, or
yeah, we told them. We told them informally that each task has a correct answer that depends on the number of urns and the number of cards, and then the number of balls in each urn. And we tell them that they'll earn the highest payoff by reporting their most accurate guess of what the likelihood of each urn is.
Without giving them actually the solution.
And then they have a little box where they can click and see the details.
Okay, thanks.
So there's been some research in terms of belief elicitation. There's different methods out there. Some of the more complicated methods that are incentive compatible from a game theoretic perspective often tend to confuse subjects if you give them these very complicated scoring rules. It's been found that the subjects get confused and they're not sure what to do. So we followed, there was this paper by Dan Vesterlin and Wilson on belief elicitation incentives in experiments, and they compared a lot of different methods and subjects' understanding. And often it's found that if you sort of tell them, look, there is a correct answer, try to do your best, and then they have a little button so some people who are curious can see the exact formula that it's elicited, that gives the most reliable data because it leads to the least subject confusion. Okay, so our theoretical framework, there's a state omega drawn from some state space, omega 1 through omega n. So n here would be the complexity of the state space. That's the number of distinct states in ascending order. So a state is just a number between 0 and 1. There's a prior P0 over the state space. There's a signal drawn from either R or B to correspond to red or blue ball. As I said, we focus on binary signal spaces. And the signal distribution is the probability of a red ball in state omega is just equal to omega. So you can think about that as pinning down the signal distribution so that that fully describes how many red versus how many blue balls there are. Right. Then there's also an objective posterior, which is just derived from Bayes' rule with respect to this information structure. And we denote that by P of omega conditional on signal S. Right, so as I said, we have a 2-stage model of belief formation. In the first stage, agents figure out which states to channel attention to over others via the representativeness heuristic. And then in the second stage, agents process information, but they have cognitive noise with respect to the parameters of the information environment, the prior, and the signal structure, a la Michael Woodford's work. Right, so what does that look like? Right, so Essentially, agents channel more attention to the representative state, the state that's the most representative of the observed signal. One thing to note is that in our information environment right here, we're always looking at a good news, bad news signal structure. So if you see the red ball, that's always going to be representative of the highest state. If you see the blue ball, that's always representative of the lowest state. So that's the class of information environments we're looking at. We also at the end have some new data that I may talk about looking at different ones, but sort of here, this is in line with the experimental studies we found, as well as a lot of studies from finance, where really the sort of the information satisfies a property, where as you see better news about a firm, that means you're going to place relatively more weight on them being a high type firm versus a low type. All right, so what that means is agents channel more attention to the more representative state. As I said here, the red ball is always representative of the high state. The blue ball is always representative of the low state. So we use Bordello and Schleifer's formulation of representativeness. The representativeness of the given state, as I said, is this relative likelihood, or so it captures the relative likelihood that the state becomes more likely after seeing the signal relative to the prior. So the representativeness weight of a particular state, omega I, conditional on seeing some signal Sj, is just the posterior, the Bayesian posterior of that state, omega I, conditional on the signal, divided by the prior likelihood of that state. So as that state becomes relatively more likely relative to the prior, it's going to have a higher representative state. As I said, the highest representativeness weight is always going to be on the highest state when you see a red ball, and the lowest representative weight in that case would be on the low state. So they're ordered according to the likelihood of the red ball in that state, but also the sort of the extremeness, or how much representativeness comes into play, does also depend on the prior and the information structure as well. Right, so as I just already said, in the case of a red ball, the urn with more red balls is more likely. In the case of a blue ball, the urn with blue balls is the more representative state. All right, so then the way they form their posterior belief is that their posterior belief, given their channeled attention, is equal to the Bayesian posterior times this representativeness weight, where parameter theta captures the severity of the distortion, or the severity of their representativeness. All right, so just one thing to highlight here, given our design, this representativeness weight is something that we can calculate explicitly. As I said, it's based on the relative likelihood of the posterior versus the prior. And this parameter theta is the one parameter from this step of the belief formation stage. So parameter theta is going to be something that we can measure and that we can estimate via parameter estimation with our belief data. Just the one thing to point out here, this z in the denominator is just a normalization factor, and that just ensures that the distribution still sums to 1. So it's independent of the state for each signal. It just divides by the appropriate factor to make sure that we actually have valid distributions here. All right, so we let PR of Sj denote our simplified posterior following signal J. That's after the attention determines which states agents focus on more versus less. And then in the next stage, the evaluation stage, given their channeled attention, they're going to use Bayes' rule to update subject to cognitive noise. Okay, so we assume they have a noisy representation of this transformed posterior. They have a prior about what the posterior should be. This is called their cognitive default, which is separate from the parameters of the particular informational environment. And then they get a signal of the parameters for the relevant information environment they're working in, and they update their beliefs, taking into account their prior and the realized information. So sort of the way you can think about this conceptually is that agents have sort of a default model in their head. They're in a belief formation task. They have this model they're working with, and then they tailor it when they're presented with a new information environment with different parameters. They do take into account those new parameters, but they don't just jump all the way to using them. They update the model in their head and move towards using them, but they stay compressed towards their prior. So that's this idea of cognitive noise, that it's either costly to constantly be adjusting the model in your head, or that agents may not fully understand things, and so they don't fully internalize parameters you give them. Rather, they have this model in their head, and then they sort of get noisy signals of how they should be updating in different new environments. So it's a model based on this idea of cognitive precision, or cognitive noise from psychology. All right, so what this looks like, or how this operationalizes, is that given agents posterior, their simplified posterior from the channeled attention, they're then what we call their subjective posterior, following a signal realization SJ, is a weighted average of this simplified posterior and their default prior, P bar 0, where this parameter lambda captures the degree of cognitive noise. So no cognitive noise, lambda equals 1. They fully internalize the new model in each setting. Full cognitive noise, lambda equals 0. They never update given the new parameters. So again, there's another parameter here. Parameter lambda is a parameter we can estimate. That's the cognitive noise parameter. So our updating model has these two parameters, theta capturing how much attention is binding for agents versus lambda capturing how much cognitive noise agents exhibit. All right, so we refer to this p hat, which is the prior belief after agents channel their attention and then update with noise, as the subjective posterior. Okay, so this is the object that we're going to be focusing on our predictions on in the theoretical framework, and then comparing to agents' actual belief data in the experiment. All right, so next, given the subjective belief, we define over and under reaction. All right, so we can say, given a subjective belief, we can compute the subjective expected state as just the weighted average of the state space with respect to the subjective belief. We can have an analogous definition for the objective expected state with respect to the Bayesian posterior. And so our measure of over and under reaction compares the subjective expected state to the subjective expected state given our model of belief formation. Okay, so we say an agent overreacts if the expected movement from their subjective posterior relative to the prior is greater than the expected movement of the objective state relative to the prior. So for example, if the prior expected state was 0.5, the expected objective posterior was 0.6, and the agent moved to 0.7, that would be overreaction. If the objective posterior is 0.6, but they only move to 0.55, that would be underreaction because they move less than the Bayesian posterior relative to the expected state. All right, so that gives us a prediction of whether it's over or under reaction. We also want a measure of over under reaction so that we can compare the degree of over under reaction across different informational environments. All right, so here we define the overreaction ratio as the difference between the expected movement in the subjective posterior expected state versus the expected movement in the objective posterior state divided by the expected movement in this objective posterior state, just to try and translate things and keep them, to account for the fact that in an environment with a lot of movement in the objective posterior and a lot of movement in subjective posterior, we want to have a measure that we can compare to settings where there's less movement in the objective posterior. All right, so here with our overreaction ratio, again, just as before, that's just, we have a similar definition up here. Overreaction equivalently in terms of the overreaction ratio is that the overreaction ratio is greater than 0. Underreaction is that it's less than 0.
Aislinn, could I ask a quick question?
Sure.
When you calculate PR and you look at that formula, it's not obvious to me that it's a lot simpler than the correct Bayesian formula. I mean, it seems to involve about as much arithmetic, unless theta is, I guess, 0 or infinity, when perhaps it'd be simpler. So how is this particular functional form, how can it be defended as a simpler?
So the idea is not that agents are actually using that formula, it's that the formula is a good model of their cognitive process. So their cognitive process is that they put more attention on the more extreme states, and then, as you said, if theta went off to infinity, that would correspond to putting all of the weight on the most representative state, which would be quite simple. But subjects, in general, people sort of smooth things out. They put too much weight on the representative states, but they don't put 0 weight on the other states. And as I'm going to show you in the data, this turns out to be a pretty good approximation or pretty good fit for what subjects actually do. So it's not that they actually are doing these computations cognitively. It's more that this is a model that captures whatever cognitive process determines how they channel their attention, figure out how much weight to put on the extreme states, and then smooth everything else to the other states. So I'll hopefully show you convincing data that this does capture what's going on. We have so once we present the initial data, we also have some tests of the mechanism. We do this by manipulating attention and showing that manipulating attention does in fact manipulate how people respond to the representative state, holding fixed the information environment. So it does suggest that the attention story is the mechanism that's causing this overweighting. And then we also have some data on the fit of the model. We look at a nice comparison of, first of all, the completeness of the model versus, so using Annie Lang and Drew Fudenberg's recent work, how well the model fits the predictable variation in the data. And then as a counterpoint, to show that the model can't explain anything, we also look at the restrictiveness of the model, which is a sense of how well could the model fit data that was just synthetic, right? So you want it to fit your actual data well, but you don't want it to fit synthetic data well, because that would suggest it could fit anything. So I'll have we do a lot of tests to figure out if we can really make a good story that this is a good way to capture agents' cognitive processes.
Are these characters in this experiment doing this once, or is it repeated?
They make 8 to 15 decisions each. So they see 8 to 15 different informational environments.
Without feedback in the middle, I guess, right?
Without feedback, yes, of course. And everything's randomized. The order is randomized.
So that there are different setup for the number of balls in each urn and all of that from over the 15, right?
Yeah, so each time they see a new information environment, it's just like what I showed you right here. So these are the instructions, and then they see this. I guess you can't see my hand, but they see this right here, described as the state space, the prior, and this, and then their posterior is elicited. And we didn't, so for given agents, when I say we manipulated the things like manipulating attention, that was a between subjects design. So the benchmark subjects just all had the standard attention where we didn't constrain attention. And then we did some things to try and constrain attention in different ways to try and really get at the mechanism. So I'll first go through the basic results, and then I'll give you some other variations we ran to, again, try and really present a convincing story that this is the mechanism, an attentional mechanism is leading to this overweighting. Okay, so that's our definition of under and overreaction. Just in the interest of time, let me skip this because I don't have much time left, but we had a couple of properties on the state space. Symmetry just means that if, say, 0.2 was a state, then 0.8 was a state as well. Similarly for the prior, 0.2 had a given weight, 0.8 had this same weight if it was a symmetric prior. More interior states just correspond to states that are closer to 1/2. And as I said, complexity is operationalized by the cardinality of the state space. Okay, so let's first look at our predictions for complexity. So let's fix 2 informational environments with a symmetric state space, uniform prior over them. Let R denote the overreaction ratio for the first environment and R prime for the second environment. All right, so our first prediction is that if we fix the extreme states and we add more interior states to make environment omega, or make state states omega prime more complex, then for sufficiently large theta, sufficiently large representatives parameter, the agent overreacts more in the more complex environment. In other words, their overreaction ratio is higher. All right, we could also similarly have the same logic would predict more overreaction or less underreaction for noisier signals. So just to quickly think about what's going on here, as we're fixing a uniform prior, we're fixing extreme states, and we're adding some more middle states. So we know that the channeled attention state means that people put more attention on those extreme states relative to middle states. That's what the extreme states are, the representative ones. And so when there's only 2 states, that's not really doing much because there's only those 2 extreme states to pay attention to anyway. But as we add more and more middle states, there should be more and more weight on those middle states. And so the channeled attention is leading to more of a distortion on those extreme states. If we're overweighting those extreme states more, that's leading to more overreaction. So that's the intuition for the theoretical result. If we look to the data, so we test this prediction by varying the complexity of the state space. We had our simple state space was just the 2 states. So we had a parameter 0.6, 0.7, 0.8, and 0.9. The state space was either X or 1 minus X, right? So we had a 0.4, 0.6 state space, a 0.3, 0.7, so on and so forth. And then we added to that state space, we added a third middle state, 0.5. Right. And then we also looked at a state space with complexity 4, cardinality 4. Here we have to keep things symmetric, so we just added some interior states, y and 1 minus y, for these parameters right here. And then our fifth state space, we took this state space of 4 states, and then we added a 0.5 again. All right, so we're always adding interior states. So we can compare 0.3 to state space 3 to 2 with this comparison. We can compare 4 to 2 because we're adding more interior states, and then we can compare 5 to 4 to 2. That's how our theoretical results rank these different parameter environments that we look at here. We also looked at many states. So we looked at 11 states, 0, 0.1, 0.2, 0.9, 1. Right, so to check out, and then we maintained a uniform prior throughout these experiments. All right, so to look at the complexity data, first of all, we just looked at the binary state space. This is averaged across all of the different state space. If we look at the fraction of people who over versus underreacted, we found that most people underreacted. So more people underreacted versus overreacted in the binary state space, which is the standard result from the lab. So first of all, we wanted to just show that we want to make a case that the complexity of the state space was driving the difference between the lab results and the macro and finance results. We first want to show that indeed in our paradigm with our subjects, we do get the standard result from the lab when we look at similar parameters to what people looked at in the lab. We can also split this out by signal diagnosticity. So here on the x-axis, we have the, this is just here, the signal diagnosticity of these different parameters we looked at, number of red versus blue balls. Here on the y-axis, we have the overreaction ratio. Remember, less than 0 is underreaction, greater than 0 is overreaction. And here, indeed, we find that across all of the signal diagnosticities we looked at, people underreact on average. All right, so standard lab result. Now let's look to the 3-state case. So here, again, at each point, we can see that once we move from 2 to 3 states, for a given signal diagnosticity, we move from underreaction below 0 to overreaction above 0. Yeah, we also remember our prediction was also that more overreaction for noisier signals. So noisier signals in this environment corresponds to signals more in the middle. And indeed, we find a higher overreaction ratio here relative to the more precise signals. And we can do the same thing. We next go to 5-state. As I said, that one 5-state is ranked with respect to 3-state and 2-state. And again, this green line right here, the 5 states, again, we find that there's more overreaction than 3 states and 2 states. All right, so just keeping uniform prior, adding these interior signals, we find that overreaction is increasing as we increase the complexity of the state space. Moreover, within each fixed complexity, we're getting more overreaction as we get to these noisier signals as predicted. Okay. Also, to bring in the 11th state, we can't really present the 11th state with these different signal diagnosticities since there's so many different states. So here again, we look at the fraction of people who over versus underreacted. And we can see that if we go from 2-state to 3-state, 4-state, 5-state to 11-state, that we started with underreaction, 3-state flipped to overreaction, and then the share of people overreacting is increasing as we increase the complexity of the state space. So it goes up again at 11 states. All right, so as I said, nearly all of the laboratory evidence focused on a binary state space. There, this channeled attention or representativeness has little bite because there's only 2 states, so there's really not much channeling that needs to happen. So underreaction is expected. The cognitive noise mechanism kicks in more. There's a couple experiments with more than 2 states, and those did actually find overreaction. That wasn't presented as the mechanism for overreaction, but there was a few that looked at more complex experiments, say a financial market where there was some fundamental value of a firm that could be, let's say, between 0 and 100, which would be many states. And again, indeed, that they found overreaction. And then, as I said, in macro, there's a large number of potential states in something like forecasting inflation or forecasting a firm's, whether a firm's stock price is going to increase by a lot or decrease by a lot. And so their overreaction is expected, which is consistent with our comparative static predictions for complexity. All right, so let me look at the other comparative statics now, since I have about 20 minutes left. So the next thing we looked at was the prior concentration. So again, let's fix two informational environments with a symmetric state space and symmetric priors. That means if you put, say, a certain weight on state 0.2, you put the same weight on state 0.8. Note here, we're fixing the state space. So we're fixing complexity here, as well as the actual values of the states, and we're just going to manipulate the prior. Okay, so again, let R denote the overreaction ratio for the first state space, or first informational environment, R prime for the second. A more concentrated prior means that you put more mass on those middle states and less mass on the end states. And so our prediction from our model is that if the prior is more concentrated, then for sufficiently large theta, sufficiently high representativeness, the agent's going to overreact more to the concentrated prior than the less concentrated prior via the overreaction ratio. Okay, so again, we test this prediction by, we fix an informational environment. We look at all of the same informational and state spaces that we looked at for the three state environment in the complexity case. So 0.6, 0.5, 0.4, 0.7, 0.5, 0.3. And we varied the prior. We looked at a uniform prior that put equal mass on all three states. We look at a concentrated prior that put mass 0.5 on the middle state and 0.25 on the two end states. And then we looked at a diffuse prior that put mass 0.4 on the extreme states and 0.2 on the middle state. So we had these three priors. Remember, our prediction is that more concentrated prior, more overreaction. So our prediction is that overreaction would be the highest for this middle one, followed by the uniform prior, and then followed by the diffuse prior. Okay, so looking to the data, this is the uniform prior. This is the data that you already saw for the three-state case when we were looking at complexity. All right, split out by signal diagnosticity. All right, now we look at the concentrated prior, just the purple line. Indeed, we find more overreaction here. And we look to the diffuse prior, and that's the green line right here. And indeed, we find less overreaction. So things move down more towards underreaction for the more diffuse prior. So again, in line with our predictions. Also here, we can see that even as we vary the prior, the prediction that we get more overreaction, so fixing a state space and fixing a prior, we get more overreaction for these noisier signals than the more precise signals holds across these different priors as well. All right, so our third prediction is in relation to an asymmetric prior in a binary state space. All right, so let's look at a binary symmetric state space. The states are symmetric, so say 0.2 and 0.8. An asymmetric prior, so different mass on the low state versus the high state. Our theoretical prediction is that if the signal is confirmatory, in other words, if you put more mass on the high state and then you see a red ball, or you put more mass on the low state and you see a blue ball, then the agent is going to underreact more, where if the signal is surprising, if it goes against the prior, then depending on whether the signal is precise or imprecise, we're going to get a comparative static on overreaction versus underreaction. So they'll underreact to more precise disconfirmatory signals, and they'll overreact to more imprecise disconfirmatory signals. All right, so again, we test this prediction by keeping the state space constant, but changing the skew of the prior in a binary state environment. So these are the same binary state spaces that you saw for the complexity treatment. Uniform prior is what we looked at for complexity. Now we look at an asymmetric prior of 0.3 versus 0.7. Okay, so here where there's a 50-50 prior, there's not really, this is the same data right here because there's not a notion of confirmatory versus disconfirmatory signals. Neither one goes against or confirms the prior. All right, so we already know from the complexity treatment that here, looking at the overreaction ratio on the y-axis, we saw underreaction. So this was below 0 when we looked at the basic uniform prior binary state environment. All right, now we find that for disconfirmatory signals, we see overreaction as predicted when we look at the 30-70 and 70-30 prior. And similarly for confirmatory signals, as predicted, we see underreaction. So here again, we see quite a bit more underreaction than we saw for that neutral signal in the 50-50 prior case. We can also split this out by signal diagnosticity. And here we see as the signal diagnosticity is noisier, we see more overreaction to this disconfirmatory signal as predicted. Whereas as the signal becomes really precise, we see a bit of underreaction. Versus for the confirmatory signal, that's the blue line right here, and we see underreaction across the board. All right, so again, as predicted by our model. All right, so these were our basic results. We had comparative statics along 3 different dimensions of the information structure: the complexity of the state space, the prior, or whether the prior was concentrated or diffuse in a 3-state environment, and then whether the prior was asymmetric or not, and then the type of signal in a 2-state environment. We saw that our data matched our predictions well. So now what we want to do is try and get a better sense of this, of the mechanisms. Is it actually attention that's generating these results, or do we just happen to find a mechanism that was similar to what agents were doing? So the next thing we do is we actually measure attention. We use a 5-state design with a uniform prior. We adopt what's called the mouse lab paradigm from psychology, which has been validated as a way to measure attention. And what it does is it tracks where subjects click first. And they find that where subjects click first is a good, is a way to measure what they're paying the most attention to. Right, so we randomize the order of the urns so that the most representative state was not necessarily the first one. And then here, when they clicked on the urn, we could see that's where they clicked first to enter their beliefs, that's where they click second, and so on and so forth. All right. So there's 2 things going on here. First of all, this is letting us measure what state they're paying attention to the most versus the second most. Is it the representative state? And then the second thing that's going on is that the paradigm itself requires attention. And so if we think of attention as a stock, then taking some attention to this paradigm to have to be clicking to enter beliefs in the way that the paradigm forces you to is going to reduce the attention stock. And reducing the attention stock is akin to increasing our parameter theta, which would predict more representativeness and therefore more overreaction. Right? So if attention is constrained, overreaction will be exacerbated. So first of all, if we look at what states are attended to first, we break this down by which state is representative. Remember, that depends on whether they saw a red ball or a blue ball. When state 1 is representative, we find that over 60% of people click on it first. Versus when state 5 is representative, we find that over 60% of people click on state 5 first. All right, so this suggests that indeed agents are paying more attention to the most representative state based on their first click data. All right, if we now look at...
Can I ask a clarification question? Sorry. So before they click, what do they know about the different urns? And so how do they... And then because you say enter, what does it then reveal when you click on it?
Oh, that's where they put in their beliefs. So they have the exact same description of the experiment as before. They know the number of balls, the number of cards, the state space. Just like in the basic treatment, the only difference now is that, they have to, before they can do anything, they have to then click and then enter. Whereas before they didn't have this, we weren't tracking their first clicks.
So then you enter basically your assessment.
Yeah, so they already know which state is representative, or they already know the information structure in the ball that they've seen when they're doing this part.
Okay, thanks.
So actually not knowing is something I'm going to show you data for in a minute as well, which has some interesting results. All right, so first of all, as we see that they are indeed paying attention to the most representative state first, as we manipulate which signal they see, we can track their attention does change. Second of all, as has been documented, documented in other studies that validated this paradigm, it does constrain attention, it does reduce people's attention. And so the prediction is that we'd see more overreaction. Here, this is our original 5-state data. And then if we look at the timing data, so this is the mouse lab paradigm, indeed it does increase overreaction, which suggests that constraining attention does exacerbate representativeness. It increases theta. And again, when we do parameter estimation as well and show that this does increase the estimate of theta. All right, also, we can break this down by who did click on the representative state first versus who didn't. That would be suggestive of people who are channeling more attention to the representative state versus not. And indeed, the blue line right here is the data for agents who clicked on the representative state first in the new experiment. This is data from the green line is now the new experiment, but people who did not click on the representative state first. And indeed, we find that people who did click on that representative state first do exhibit more overreaction than those who didn't. So again, suggesting that this attentional mechanism, if agents are paying attention to that more representative state first, it is causing them to overweight it more. All right, so let's see. The next thing we do is we turn off representativeness. So same design, but now they don't know which state is represented when they click on something. So we basically shut down that ex-ante information in order to see the value of each state. In other words, the number of red versus blue balls. Now they have to click on something to see it. So this is the idea here, is that it's not just really obvious to look at the information structure before you enter your beliefs and see which state is representative. All right, so this generates uncertainty over which state is representative. It's more difficult to channel your initial attention to the representative state if you can't see it until you click on it. This is just to highlight, it's the same underlying setting as the baseline experiment. So 5 states, uniform prior, same signal diagnosticity. They can fully understand the environment by clicking reveal for each of these. So nothing is hidden. They just have to put some effort into learning it. All right, so now we find that when we turn off representativeness by not making it immediately obvious what state is representative, we find that now their percent first click is just evenly distributed across the states. So A, B, C, D, E. They still are seeing, once they click on that state, they're still learning the number of red versus blue balls, but they can no longer just easily channel their attention to the representative state ex ante. All right, so in this case, if we shut down representativeness, our model would predict underreaction from the cognitive noise, even though it's the same information structure. And that's exactly what we find. So this right here is the green line right here is the original one where you had to click, but you already knew which state was representative. Here, this red line right here is where you had to click, and that's where you could learn what the distribution of the states are. So we find, again, underreaction here when we are able to shut down the representativeness by making it hard to see which state is representative. So we find it, actually, we even find it goes back to underreaction, as is found in standard lab experiments. So again, this suggests that attentional mechanism, if we can shut down the way that agents had this easy way of channeling attention when they first see the information structure, we can shut that down. It does, and then find underreaction. It really does suggest that it's attention that's driving this representativeness to cause the overweighting of the extreme states. All right, so I think I'm going to skip this part just because I only have a few minutes left, and there's a couple other things I wanted to discuss. But the next thing we do is we assess predictions state by state. So we look at the actual belief data instead of the overreaction ratio. All right, so you might say, like, one of the key contributions I think of our paper is looking at the interaction between 2 psychological mechanisms. So a lot of the literature focuses on exploring one psychological mechanism at a time. And what we show is that really we need these 2 together. We get a much more parsimonious model of belief updating if we look at these 2 mechanisms side by side. We can make predictions across many different informational environments. So often in the lab, people just use a cognitive noise model that fit relatively well in the binary state data. Often in the macro and finance data in the field, people use representativeness but not cognitive noise. And it fit somewhat well, but there are also some things that wouldn't be explained. And we show that bringing these 2 together actually gives a very parsimonious model of the way that beliefs move in response to different informational environments. So let's look at raw belief data. Instead of looking at the overreaction ratio, we'll look at the actual probability distributions. Here we'll do this across 4 states. What we have here on the y-axis is the difference between the subjective posterior via our model or via the data and the Bayesian benchmark right here. Right, so then states 1, 2, 3, and 4. All right, so we're going to look at the case where the agent saw a red ball. So state 4 was representative. Cognitive noise would predict that agents would put less mass on the 2 highest states and more mass on the two lowest states following a red ball relative to the Bayesian posterior. So this is the predicted difference between the subjective posterior from only cognitive noise, setting theta equals to 0, versus the Bayesian benchmark. We can do the same thing for representativeness. Representativeness would predict that agents would put a lot more mass on this representative state relative to the Bayesian benchmark, but also that they'd put less mass on this lowest state, these lowest two states. Depending on the information structure, sometimes they may put more mass on the third state as well, sometimes less, depending on how extreme the bias is and also what the information structure is. But really the key thing here is that it's always less mass on state 1, always more mass on state 4 relative to the Bayesian belief. What does our two-stage model do? Well, our two-stage model, the representativeness also drives excess mass on state 4 because of representativeness, but it also, because of the cognitive noise, remember cognitive noise predicts more mass on the low states, less mass on the high states. Those two interact to predict, in our model, more mass on the two extreme states, much more on the representative state than state 1, and then less mass on the middle states. So of course, balance things out because the excess mass has to sum to 0 since it's a probability distribution, and we're taking the difference with the Bayesian belief. Right, so this is the prediction of our two-stage model. If we now look at the raw belief data from our experiments, again, we find the excess mass on state 4. We also find some excess mass on state 1, and then that's counteracted by less mass on the two middle states. Right, so again, if we just look at the state-by-state beliefs instead of taking a statistic, the overreaction ratio, again, we find that the interaction between these two mechanisms really predicts the pattern that we see in the data. All right, so this is just for one information structure, but if we look at these patterns are robust across all of the different informational treatments we look at. So this is strong evidence for what we call a cognitive complementarity. Really, we need the interaction between these two mechanisms to get the strong predictive power that we have. All right, in the last couple of minutes, I want to also show another thing that we do to try and understand the explanatory power of our model. And so we use a new method by Drew Funenberg, Annie Liang, John Kleinberg, and Sendel Mullainathan that tries to quantify the completeness or added value of a model relative to some benchmark. And so what this does is it tries to say, well, is there predictable variation in the data that you could capture via a model? How much of that are you capturing relative to the benchmark of what Bayes updating would capture? So you can think about, in regression analysis, an R-squared is a measure of a fit. An R-squared captures two things. It's how well does your model fit and capture predictable variation. Also, how well does it fit and capture, is there a lot of noise in the data? And so essentially, relative to an R-squared, completeness is shutting down the noise. It's parsing out the noise to say, look, you could have really noisy data. You'd never fit it well, but are you fitting what you can fit? Are you predicting what is predictable in the data? And they use machine learning to do this. Right, so the definition of completeness, you look at model fit, it's a loss function. So we use a Kullback-Leibler divergence since we're looking at probability distributions. We look at the difference between the expected loss of a given model. What this completeness statistic right here is it looks at the fit of Bayes' rule relative to the best fit of our model. So that's looking at our model across all values of theta and all values of lambda. It's doing a parameter estimation to figure out the best parameters for our model across all information treatments. So that's something that's with theta and lambda, we estimate across all information treatments as fixed. We don't tailor it to each one because that's too much flexibility. And we say, what's our best fit of our model across all of the information environments we look at? That's this, what's the error when we have the best fit of our model? And then we compare that to what's the error of Bayes' rule versus this F star, which is the F star is the quote unquote true mapping. And that's something that you learn completely model free, but it's from machine learning. So you run a machine learning algorithm on your data and say, what's the best fit that a machine learning algorithm can have? So essentially you're comparing how much better is your model to Bayes' rule relative to how much better is a machine learning algorithm to Bayes' rule as they capture, obviously, even with machine learning, if you have noisy data, you can't predict that. And so this is the measure of sort of the best, quote unquote, predictable variation that you can have, shutting out the noise. All right, so just a couple of properties of this. First of all, it's a measure between 0 and 1. If you're no better than Bayes' rule, your measure will be 0. If you're as good as the true mapping from machine learning, your measure will be 1. And so, as I already said, it's the predictable variation that our model is capturing relative to the maximum possible. All right, so I'm not going to go through how we actually estimated that. We used the procedure suggested by Drew and Annie in their paper. And so here's what we find. First of all, we look at just two states, because that's what had been done in the literature, the two-stage model, compared to a cognitive noise only model. So we shut down representativeness, theta equals 0, and just look at cognitive noise only. We also shut down cognitive noise, lambda equals 0, and we look at representativeness only. And so we can see that for two states, our model has high fit, it's 1, which is the highest possible, but so did cognitive noise. As we said, there was underreaction when we looked at two states. Cognitive noise did pretty well explaining that as well. Representativeness was no better than Bayes' rule. But once we go to more than two states, the fit of the cognitive noise model drops down to 0.36 from 1, but the fit of our two-stage model stays high at 0.92. Versus representativeness, again, is no better than Bayes' rule on its own. But really, representativeness added to cognitive noise makes the fit of the model jump from 0.36 up to 0.92. So again, this is really strong evidence for this cognitive complementarity. Representativeness on its own is no better than Bayes' rule. Once we look at these more complex environments, cognitive noise doesn't do very well either, but together, both of them have a very high fit in terms of capturing the explainable variation in the data relative to the best fit possible. Right, now you may say that, this could just be because there's too much flexibility once you have two parameters versus one. We look at that, we have a measure of what's called restrictiveness, which is looking at how well could your model fit any random data, not your actual data, just any random data. If it could fit any random data well, that's bad because it suggests that your model is too flexible or doesn't have enough, is not restrictive enough. So here we look at, again, another measure developed by Annie and Drew, as well as Wayne Wow. Our measure, again, is between 0 and 1. If the measure is 1, it fits synthetic data no better than Bayes' rule. So in other words, it's as restrictive as Bayes' rule. If it's 0, your model can fit synthetic data perfectly. And so in other words, it's flexible to fit any sort of random data out there. Okay, so we look at this, we find Bayes' rule has a completeness of 0 by definition, that's our benchmark. It has a restrictiveness of 1, again, by definition, that's our benchmark. When we look at cognitive noise only, this is, we do get, as we said, more completeness, but not much. We don't lose much restrictiveness here, so we go down from 1 to about 0.95. Now, when we add in our two-stage model, as we saw previously, we get a lot more completeness. This is the red dot right here. We jump up to above 0.9, but our restrictiveness still doesn't fall very much, so it stays very high. It's not that much less restrictive than Bayes' rule. So the reason our model is fitting so well is not because it can fit any data, but because it is capturing some of the predictable variation while still maintaining high restrictiveness. It doesn't do a good job fitting synthetic or arbitrary data. All right, so I think I'm just about out of time. So let me just quickly summarize. All right, so we develop a framework that incorporates multiple psychological mechanisms. We predict over versus underreaction as a function of the informational environment. We showed that overreaction emerges more in complex environments with concentrated priors or disconfirming signals. We see more underreaction for simple state spaces, diffuse priors, or confirming signals. And we provide support for our predictions, including evidence suggestive that attention does, in fact, guide what people are over versus underreacting to. And we also look to figure out a way to have a methodology that we can have a unified approach to model these multiple psychological phenomena simultaneously and understand how they interact with each other, both to give us a more parsimonious theory and also a more complete picture of how people are actually forming their beliefs. And so this combination of mechanisms also does help us rationalize prior findings on over versus underreaction across a variety of domains. Lab experiments versus macro data. Also, some of the few lab experiments that did find overreaction did have these more complex environments in different ways. And so it suggests that really this complexity does help organize whether overreaction versus underreaction emerges. Great, so that's it. Sorry, I'm a few minutes over, but thanks so much for your questions.